Welcome and settle in. Imagine yourself in a cool, quiet cavern where every sound is softened by stone and a careful drip, drip, drip measures time like a patient metronome. Tonight, we lean into the unhurried rhythm of caves and the quiet, almost invisible geochemistry that grows stalactites, grain by grain, layer by slow layer. If this calm corner of science helps you unwind, you can gently tap like and subscribe. And if you want a peaceful path of learning as you drift, there is a playlist link in the description so the next calm story will follow without you lifting a finger. How sleepy are you on a scale of 1 to 10? You are comfortable now, perhaps settled under a blanket, breathing softly. The light around you is dim. The cave is not a place of hurry. It is a place of patience, where time pools in shallow basins and spills over in long, slow arcs. You picture a ceiling above you with a pale bead of water gathering at a rocky tip. It swells, clear like glass, then trembles and vaults. It lands on a smooth stone floor with a lazy tick, so subdued it seems to occur somewhere inside the rock itself. That tiny drop carries with it a whisper of the outside world, a trace of air from the soil, a thread of carbon from a leaf that fell last year, and a dusting of minerals from ancient seas that became limestone long before any familiar map existed. This is how a stalactite grows. Not with haste, not with drama, but with endless repetition and with the soft chemistry of water, gas, and stone. You can imagine the journey of a single drop. It starts as rain or melted snow falling through air that cradles carbon dioxide. On the way down, a small amount of that gas dissolves into the water. Nothing abrupt happens, just a gentle pairing of water and gas that forms a mild carbonic solution. This is not a strong acid. It is a quiet one, a nudge rather than a shove. Then the water meets the ground. In the soil, life is slow and busy at the same time. Roots breathe, microbes dine on remnants of leaves and the remains of stems. They exhale carbon dioxide, and the air in that thin layer of soil becomes richer in it than the air above. The drop lingers here and becomes a little more charged with dissolved carbon dioxide. It moves on, pressed by gravity, into fine pores, into hairline fractures, into pathways drawn by centuries of flow. Beneath the soil lies limestone, a rock made almost entirely of ancient shells and marine skeletons compacted into a bed of calcium carbonate. The water that carries carbon dioxide meets the calcium carbonate the way a soft brush meets chalk. It dissolves a little with a chemistry so simple and elegant that it feels like a lullaby. The water takes up calcium and bicarbonate, cradling them in solution. A piece of the rock becomes invisible, but it is still there, just carried forward. In the quiet darkness of the rock, the water moves slowly along, and in time it reaches an opening where the air is cave air, cooler, stiller, and often poorer in carbon dioxide than the soil air above. This difference matters. It is where the direction of the story shifts. When water rich in carbon dioxide meets air with less of it, the dissolved gas begins to leave the water. The drop sits on the ceiling, and the carbon dioxide, patient but persistent, slips out of the liquid and into the cave air. As the gas leaves, the water becomes a little less acidic, a little more ready to accept carbonate, and the calcium and bicarbonate it carries can come together again. A thin film of calcite, the crystalline form of calcium carbonate, takes shape on the surface. At first, it is delicate, a rim around the edge of the drop. With time, ring after ring piles on in a downward growing straw, a fragile tube called a soda straw. You picture the circle of the tube extending, one tiny ring per drop, the tube hollow at its center, with water flowing gently through it and dropping from its tip. The gentle rhythm continues. If you imagine staying perfectly still and watching for months, years, decades, the soda straw slightly thickens. Sometimes a stray gust of air or a small tremor breaks the fragile tube and the rim collapses, so the water spreads and deposits more broadly, building a carrot-shaped stalactite instead. Other times, the straw remains intact, a glassy narrow tube many tens of centimeters long, hemmed with faint growth bands that catch light like the grain on driftwood. In high humidity, which is the usual gift of caves, evaporation plays a minor role. The main actors are the carbon dioxide that leaves the drop and the quiet saturation of water. With respect to calcite, the water is said to be supersaturated with respect to calcite at that spot, meaning that replacing dissolved ions with solid crystals is thermodynamically favored in the gentle way that a ball sitting on a shallow slope will roll if nudged. Each drop that pauses and departs leaves behind a dusting of solid mineral. The stalactite becomes the memory of many drops. You might like to picture the cave itself. It is not an empty vacuum. It is a breathing space with narrow connections to the surface that allow air to exchange slowly. In winter, cooler, denser air may slide inward along low openings, while in summer, warm air may rise it out. The breathing is subtle, but it influences the carbon dioxide in the cave air, and therefore the rate at which water can lose its dissolved gas and deposit calcite. When the cave air has higher carbon dioxide, the drop loses less. When the cave air is leaner in that gas, the drop loses more. So the stalactite, without intention, listens to the seasons. Its growth rate traces the rhythm of air density and the pace of recharge above. It remains still, but it records motion. The chemistry of calcium carbonate precipitation has many quiet thresholds. One of them is the saturation index, a measure of how ready the water is to deposit calcite. Another is the presence of certain ions that nudge the crystal form toward calcite or toward its sibling, aragonite. Magnesium ions, for example, favor aragonite by interfering with calcite growth. The ratio of magnesium to calcium in the water, the presence of sulfate, the temperature, and the pH all tilt the balance. Many stalactites are calcite, whose crystals stack in rhombohedral forms like tiny slanted boxes. Some are aragonite, whose crystals are needle-like and can make feathery or frothy textures. Sometimes the cave grows helictites, strange curving forms that curl sideways and upward, guided by capillary forces, slight air currents, and the careful balance of supply and evaporation in their microenvironment. They are delicate scribbles in stone, while stalactites are the long commas that hang down, pausing the sentence of the ceiling. If you imagine touching the surface of a stalactite gently, it would feel smooth but finely textured, like porcelain with a faint grain. Over years, dust settles and becomes encased. Tiny inclusions wind up in the layers. Under a microscope, growth bands appear as subtle variations in translucence, sometimes luminous, when illuminated with ultraviolet light. These luminescent bands can reflect organic molecules that were present in the drip water, slowly degrading over time, and they can be used to trace subtle changes in the environmental conditions above. The object that seems so inert is in truth a layered record of flow, air, living soil, and the chemistry of water meeting stone. It can be calming to imagine the carbonate system in its full softness. In water, carbon dioxide and water molecules form carbonic acid. The acid partially dissociates, giving bicarbonate and hydrogen ions. If the conditions allow, bicarbonate can further release a hydrogen ion and become carbonate. The balance among carbon dioxide, carbonic acid, bicarbonate, and carbonate shifts with pH, temperature, and the amount of dissolved carbon dioxide. With higher pH, carbonate becomes more available, and calcite is more likely to grow. With lower pH, calcite tends to dissolve. The dissolved calcium and carbonate species together are called dissolved inorganic carbon in carbon chemistry, and the total capacity of the water to neutralize acid is called alkalinity. These words are soft handles for the same quiescent story. A drop of water, a reservoir of carbon in the air and soil, and a rock made long ago from shells that once floated in a gentle sea. Outside the cave, the story loops into the broader carbon cycle. When calcium carbonate dissolves under the influence of carbon dioxide, it carries carbon from the air and soil into the water. When calcite precipitates inside the cave as a stalactite, the carbon from the bicarbonate is partly returned to the gas phase during degassing and partly becomes solid in the stalactite. On long time scales, the balance reflects larger flows in landscapes and oceans, but inside the cave, the experience is more immediate and tactile. You can hear the drop. You can almost feel the faint tremor as it lands. It is a small transfer of mass, a careful restitching of stone. An attentive ear can find meaning in the rate of dripping. When the drip rate is very fast, water has less time on the ceiling to lose carbon dioxide and precipitate calcite. So more of it falls to the floor and nurtures a stalagmite below. When the drip rate is very slow, each drop has more time to dégage and deposit, and the stalactite grows a little more. If the air current is steady in one direction, the calculus shifts again, tilting growth and encouraging draperies, thin sheets of calcite that hang like curtains. When water flows along an inclined ceiling, ripples of calcite can grow like the pleats in a fabric. In this environment, the tiniest biases accumulate. Minute angles matter. A fraction of a degree can guide a century of growth. Now imagine that you are standing at the entrance of the cave and the day is warm outside. As night falls, cool air sinks into the entrance and a gentle flow is established. Inside, the temperature responds slowly because the surrounding rock is a great reservoir that changes little from day to day. Drip water is cool and even, shaped by the temperature at the depth where it traveled. Because temperature influences how much carbon dioxide can be held in water, and because it also affects how quickly reactions proceed, each degree shifts the pace of growth. Cooler water holds more carbon dioxide, so it may come in with more of the gas dissolved and need more time to dégage before calcite grows. Warmer water holds less and changes more quickly. The stalactite does not act, but the conditions around it do, and their changes leave a soft signature. For those who gently read the record locked in speleothems, the isotopes of oxygen and carbon are like two quiet voices. Oxygen isotopes, expressed as a ratio of heavier to lighter forms, reflect the temperature and the moisture source history of the water that fed the stalactite. When temperatures are lower, calcite tends to incorporate relatively more of the heavier oxygen, and the signature shifts in a way that can be interpreted carefully with attention to local patterns. Carbon isotopes tell a story about the source of the carbon in the dissolved inorganic carbon pool. Carbon from plant respiration in soils bears a particular isotopic fingerprint, and it differs between landscapes dominated by different plant types. As water percolates, and as calcite is precipitated before reaching the cave, the isotope ratio can be shifted by processes known as prior calcite precipitation and by degassing. Reading this record is like listening to a whisper through a door. The signal is faint and layered with echoes, but there is meaning if one approaches with patience and context. The stalactite grows by crystal growth processes that are universal and gentle. On the microscopic surface, steps advance as ions attach to edges. Nuclei form as small clusters of atoms or molecules become stable enough to persist, and once they have, they can grow by receiving more calcium and carbonate from the water film. The rate is guided by the degree of supersaturation, by temperature, and by the availability of places for ions to land. Impurities, such as magnesium, strontium, or organic molecules, can slow or redirect growth by lodging at the surface or near it, making some directions less favorable. The result is visible in the microtexture. Some stalactites show fabrics called columnar, where crystals are aligned columns, while others show mosaic textures, a patchwork of many orientations. Under a slow light, these fabrics look like quiet maps. Picture a stalactite that has been growing for 1,000 years. Its length may be a meter or a little more. Its diameter near the tip may be a few centimeters. If you were to slice it, which we will not do in our quiet thought, you would see layers like tree rings, but less regular, each one a diary entry of a dripping season. Some bands might be more porous, made in a time when water carried less calcium and the growth was slower. Some bands might be denser, a time of richer flow. Occasionally, a thin dark line might appear, a moment when dust from a dry season settled, or a brief pause in growth. The stalactite is a patient accountant. It keeps the ledger in calcite. Above the cave, the landscape shifts over time. Trees grow and are replaced by other plants. A meadow changes soil structure. A field is tilled and later restored. Each of these influences the air in the soil, the conductivity of water through the ground, and the carbon that drip water carries. In the vadose zone, the unsaturated rock above the water table, water moves along pathways shaped by fractures and pores. Some pathways carry water quickly after storms in pulses that fill the cave with many drops. Others are slow seepage routes, feeding the stalactite steadily even in long dry periods. Mixing between fast and slow waters blends signals. This mixing is not dramatic, it is gentle, and it smooths sharp events into soft curves. Inside the cave, there are caretakers that are not human. Thin biofilms of bacteria and fungi sometimes coat the surfaces where water lingers. They can influence the local chemistry by taking up or releasing carbon dioxide and by offering surfaces to nucleate crystals. Some microbes favor calcite growth by drawing down carbon dioxide. Others favor dissolution by releasing acids in tiny amounts. This microlife is a subtle layer in the story. It is often present, but its touch is light compared to the broader arcs of degassing and saturation. Still, if you listen closely with the mind's ear, you can imagine a chorus at the edge of the drop, a community small in size but significant in contact. As the stalactite grows, the drop that hangs from its tip becomes part of a self-regulating arrangement. The shape of the tip controls how the drop stays attached, how it spreads as a thin film, how it affixes to a small rim before falling. Surface tension holds the drop like a clear jewel until its weight is just enough to overcome that grip. Then it falls, often following the narrow bore of a soda straw or descending from the end of a broadened tip. The diameter of the straw, the wetting properties of calcite, and the slight impurities that roughen the surface all set the time between drops. If the supply of water increases, drops can form more quickly, and the film may become thicker, changing the path of dissolution and precipitation across the tip. Each tiny change feeds back into the growth in a way that is slow and soothing to think about. It helps to imagine the materials involved. The ions are not ideas. They are small charged entities with predictable behavior. Calcium is a stable, doubly charged ion that readily pairs with carbonate, itself a triangular arrangement of atoms with a double negative charge. Though in water, this is distributed across a family of forms where bicarbonate dominates at the pH of most drip waters. The lattice that grows is ordered in a regular pattern, but this order tolerates the occasional presence of magnesium or strontium in place of calcium, or small imperfections at boundaries where crystals meet. When the boundary is reached, a defect is locked in place and the crystal grows around it. Later, if conditions are right, a vein might open as water finds a new path, followed by a thin layer of clear calcite sealing it. Under light, these veins shine like hair-thin glints. Sometimes stalactites carry small, concentric, ball-like masses within them, little beads called cave pearls, forming where drops agitate fragments in shallow pools, coating them with calcite in many layers. Sometimes draperies ripple, and stalactites merge into flowstone, a sheet spreading evenly over a surface. All of these are versions of the same chemistry, expressed through different patterns of flow and surface shape. You can picture a spectrum of forms between a simple straw and a multi-tiered flowstone curtain, each part built by the same process of water meeting carbon dioxide and calcium carbonate at a boundary. On a time scale of many human lifetimes, the stalactite becomes a record for science. When carefully sampled and dated, often using the ratio of uranium to thorium in the calcite, the layers can be placed along a calendar that reaches back tens to hundreds of thousands of years. In those layers, chemical signals are read like muted sentences. An increase in magnesium relative to calcium may hint at a time of slower water movement in the rock above. allowing more prior calcite precipitation to occur, which removes calcium and makes the remaining solution richer in magnesium. A change in oxygen isotopes may indicate a shift in temperature or moisture source, but the signals are subtle and must be interpreted with caution. Caves are local places. Each one has its own breathing pattern, its own hydrology, its own nuance. The meaning rests in context. The flow of air through a cave also carries faint traces of the world above. When outside air pressure dips or rises, when winds change direction, when a cold front slides in, the cave senses these movements. The carbon dioxide in cave air can rise when many visitors enter, exhaling and stirring the air. It can drop in seasons when ventilation is strong. These changes tune the rate at which drip water can decay. In some caves, the rates of stalactite growth vary on daily, seasonal, and long-term cycles that reflect the breathing of the earth. In others, the slow architecture of rock keeps the cave more isolated, and the changes are muted. In either case, the stalactite remains fixed and patient, the tip always just below equilibrium, receiving from each drop what it is ready to hold. If you slow your imagination further, you can feel the thermodynamic landscape that guides the process. The water and carbon dioxide want to reach an equilibrium with the cave air. The calcite wants to reach a state where no more can dissolve or precipitate at that moment. The steps that connect these wants are the rates of transport and the kinetics of surface attachment. Diffusion of carbon dioxide through the thin water film is leisurely. The steps on the crystal surface advance by absorbing ions that wander through the film to them. At the edge of a step, once an ion is placed, the free energy drops a little. If a kink site is present, a corner on the step edge, the drop is more. These are subtle changes, like the gentle release you feel when you set down a book after a long day. Over millions of placements, the stone grows. Many caves around the world have stalactites made of calcite that is so pure it is translucent. Others carry iron oxides that lend warm earthy tones, from pale yellow to russet. Manganese can add darker hues, raising gray to near black. The color records the small amounts of these elements in the drip water and the oxygen availability at the time of deposition. Clear calcite forms in conditions with fewer impurities and often with less organic matter. Stained calcite suggests a different pathway. This adds a visual layer to the rhythm of growth, like an artist's brush that shifts pigment as the seasons change. You can imagine the stalactite as a canvas that paints itself, one drop per stroke. In some caves, aragonite stalactites, delicate and needle-like, form in areas where the drip water has a higher magnesium concentration, where evaporation is slightly stronger, or where the temperature and chemistry tilt the balance away from calcite. Aragonite can transform to calcite over long spans, but often it remains, preserved in a microclimate that prevents dissolution and replacement. Its crystals are lenticular, arranged in sprays and bands that catch moisture like the fronds of a fern. The tactile quality of these forms is different. They seem softer in outline, but sharper in touch. The same balance holds nevertheless. Carbonate from dissolved limestone, delivered by water, placed on stone in a long, patient cadence. Because stalactite growth is slow, any event that leaves a clear trace can be used as a marker. A volcanic eruption that casts fine ash over a wide area might leave a narrow band of tiny glass shards, identifiable under a microscope. A period of wildfire above a cave might deposit faint soot deep in the soil, some of which could be washed down and sealed in a layer. Land use changes might increase erosion and raise the amounts of detrital particles entering the cave. But even these events are rendered softer by mixing and by the smoothing of time. The stalactite is a kind recorder. It averages short, abrupt changes into a longer, calmer lesson. As you let the sound of the drip settle into your thoughts, consider the gentle interplay of Henry's law and the cave atmosphere. The amount of carbon dioxide that water holds at the surface is proportional to the partial pressure of carbon dioxide in the air. In the soil where carbon dioxide is high, the water holds more. In the cave where it is lower, the water lets it go. This pressure difference is like a quiet gradient that the system follows. The rate of flow along that gradient depends on how thick the water film is, how quickly the air moves past, and how warm the water is. When the cave air is still and humid, the film can hold on to the departing carbon dioxide a little longer. When air is moving, the gas leaves more easily. Each of these adjustments is small over the time scale of a single drop. Over the time scale of years, the pattern sums to the centimeters of growth you can see. Sleep often comes when a pattern is steady and predictable. The stalactite is an image of this steadiness. The growth hardly changes year to year, yet over centuries it becomes impressive. When you imagine the weight of it, remember that most stalactites are surprisingly light for their volume, with fine pores and occasional trapped voids within. This porosity forms because not every part of the surface is fed equally, and because small bubbles of gas can be trapped and later sealed. Over time, those pores can be filled by later generations of growth. So the stalactite both stores and refines itself, smoothing its own history as it extends. In some places, caves carry rivers of air. A higher entrance and a lower entrance create a chimney effect where warm air rises and pulls cooler air in, or cooler air sinks and draws warm air down. This motion can guide the shape of stalactites by nudging the drops slightly, so that the growth favors one side. The result is a stalactite that is not perfectly symmetrical, a little teardrop drawn to the side, a touch of motion in a still form. If you were to trace the contour of such a stalactite with your eyes, the curve would be gentle and asymmetrical, like a leaf that grew in a steady breeze. Scientists who study these forms measure drip rates with tiny sensors, capture drip water in small cups, and analyze its chemistry. They measure electrical conductivity as a proxy for dissolved ions. They measure high temperature and carbon dioxide concentration in the air. They record the rate of calcite growth by weighing plates or by measuring the length change of a straw with careful tools. The work is precise, but never hectic. The cave sets the tempo. The colleagues move quietly, write notes, and leave with the lights lowered to let the cave return to darkness. The data they bring back is a ribbon of numbers that maps onto slow time, opening a view into climate that is otherwise hard to observe. It is not a dramatic picture. It is a long and dim canvas that takes patience to see. If you sit with the chemistry a little more, another layer appears. When water dissolves limestone in the soil and rock above, it is not just taking up calcium and bicarbonate. It is also passing along trace metals and metalloids. Strontium and barium can substitute into calcite, each leaving a quiet fingerprint. Uranium, in tiny amounts, enters the carbonate lattice more readily when water is oxidizing and carries certain complexes. And it is this inclusion that allows dating later using the decay to thorium, which is insoluble and stays in the solid. The rate at which this occurs is entirely natural and extremely slow, and the measurement is gentle, using fragments of the spirit of a rock to infer its age. The sense of time stretches and softens like a long breath. You're still in the cave in your mind, perhaps standing near a flow stone that looks like a frozen waterfall. Water sheets over it in a thin layer, leaving behind a smooth lid-like surface where ripples become stone. The sound here is a whispering murmur rather than discrete drops. The chemistry is the same. Supersaturation governs deposition. Carbon dioxide diffuses from the film into the air. The color and transparency tell you something about impurities and about the current. In one spot, a tiny stalactite drips onto a hypnotic circle on the floor, building a low stalagmite with a flat top that mirrors the ceiling. These pairs are like hands reaching for each other slowly through time, and sometimes they meet to form a column that connects roof to floor, stiffening the cave like a pillar in a quiet hall. Around this midpoint of our walk, in the hush between descriptions, a small invitation returns. Still awake, comment the secret word nebula. Now, you can let your thoughts drift, keeping only a thread with the stalactite. You can picture the thin skin of water that coats the tip as an almost two-dimensional river where ions drift. You can imagine a tiny terrace forming at the rim of the drop, a step that gathers more material as the drop swells and finally falls. The timing, the rhythm, the size of each deposit all form a statistical pattern that persists even when there is noise from storms, or from a dry spell, or from a seasonal shift in the breathing of the cave. Over long times, the random parts cancel. The stalactite remembers the mean. Imagine touching the cave air. It is near saturated with moisture, cool against your skin. In the light carried by a researcher, you can see the breath of the cave as mist when it meets warmer air at the entrance. In the deep chamber, there is none of this. There is only quiet. The air there is still, and your steps feel heavy on the soft clay floor. In this chamber, stalactites are many. Some are thick and ancient. Some are slender and young. Their tips glisten. The beads form and fall. Metallic traces give a faint tawny color to a few of them, as if tea had stained the stone. Others are glassy and clear, showing faint ribs along their lengths. The ribs are the subtle marks of pauses, perhaps seasonal, perhaps tied to changes in water supply above. We can think about the ways water reaches the ceiling. There are fractures that open when the rock bends, tiny faults that draw water like capillaries in a sponge. There are bedding planes, horizontal layers, that are less cemented than the ones above and below, making a thin river inside the rock. There are joints, formed by release of stress long ago. All of these pathways converge at places where the rock is weak, and a stalactite chooses that point by simple inevitability. It grows where the drop forms. In another place, the drop forms a centimeter away, and a different stalactite grows. The map of the ceiling is a map of weakness and of small-scale permeability. Over time, as growth changes the surface, the path adjusts too. The stalactite can move a little, pivoting its point of growth along the surface, and you can sometimes see where growth has shifted by the faint, abandoned tracery of earlier deposition. The structural strength of a stalactite increases as it thickens, but at the tip, it is always fragile. A touch can break the soda straw, and even a slight vibration can crack a thin portion. This fragility in the present is in contrast to the weight of time in the whole. The stalactite teaches patience by its mere existence. It grows at rates measured in tenths of millimeters per year if conditions are favorable, slower if they are not. In some very humid and stable caves, growth can be faster, but still never fast in terms a hand would notice. When you look away, nothing has changed. When you return after a decade, almost nothing has changed. After a century, there is a detectable difference, but only if you care to remember. The stalactite prefers forgetfulness. That way, it can always be itself. The role of pH in this system is gentle and profound. A small increase in pH, making the water less acidic, shifts the balance of carbon species toward carbonate. This makes it easier for calcite to precipitate. Within the cave, when carbon dioxide leaves the drop, the pH rises a little, and precipitating calcite leaves behind a cloud of hydrogen ions in the water film that slightly counteracts the increase, establishing a soft equilibrium. The surface acts like a buffer. Alkalinity, which is the water's capacity to neutralize acid, sets how much change in pH will result from a given amount of degassing. Higher alkalinity means more resilience. Lower means more sensitivity. This quiet balance is what keeps the system stable, even when conditions outside change. There is also an aspect of texture that comes from flow regime. If drops fall infrequently, the water film has time to thin, and deposition may be more at the rim. If drops come quickly, the film is thicker, and deposition may be more evenly spread. In many cases, small ribs form where slight perturbations in flow become fixed. Sometimes airflow in the cave introduces a bias that makes the drop detach at a preferred spot, building a delicate fin. Over time, these features can become pronounced enough to give the stalactite a characteristic silhouette. A soft light will reveal these subtleties like a reading lamp brings out the grain in wooden furniture. When calcite precipitates, tiny amounts of heat are released, as the formation of a solid from ions is exothermic. In the cave's cool darkness, this heat is minuscule and dissipates quickly into the thin water film and the rock. It is a detail too small to feel, but it exists. The crystal that forms acquires a small memory in the alignment of its lattice. In some circumstances, crystals twinned together share mirror-aligned domains, creating delicate internal patterns. These are aesthetic to those who study them under a microscope and are irrelevant to your falling asleep. And yet knowing they exist can give you a soft sense of order inside apparent simplicity. Trace elements such as strontium and barium are incorporated into calcite in amounts that depend on the temperature, growth rate, and the composition of the supply water. Magnesium, because of its small ionic radius and strong hydration shell in water, fits less easily into calcite and slows growth when abundant, while at the same time making aragonite more competitive. This interplay affects the fabric, the structure, and the speed. In a cave with dolomite in the bedrock, magnesium can be more plentiful. In a cave under a pure limestone, it can be less so. The presence of clay in the overlying soil can also influence water chemistry by exchanging cations. Each of these small influences adds a shade to the stalactite's record, like an extra note in a quiet chord. When scientists interpret the isotopes in stalactites, they also consider kinetic effects. Rapid degassing and rapid precipitation can cause isotopic fractionation that deviates from the values expected at equilibrium. This means that the isotope ratios recorded do not simply reflect temperature and water source, but also how quickly the drop lost carbon dioxide and how quickly the crystal grew. That is why drip rate, cave ventilation, and the geometry of the stalactite are part of the reading. To address this, scientists sometimes build in-cave experiments where they lay plates under drips to grow thin layers of calcite under known conditions, establishing a calibration. When you step back and look at the care involved, it is like listening to a quiet musician practicing scales to understand the acoustics of a room before performing a piece. Sometimes the stalactite is visited by a small change in the path of the water above. A new fracture might open, diverting some flow. The drip becomes less frequent and growth slows, or a clog in a fine pore dissolves and the drip becomes more regular. The stalactite responds without intention. It embodies the new pattern. The tip shifts slightly, the growth ring moves, the color changes a shade. If the cave has many stalactites fed by the same water source, one can see a synchronous change in several of them. This is how the cave teaches us about the coherence of water pathways. But these changes happen gently. The stalactite carries on. If you are still with the cave in your mind, the darkness feels friendly now. You are not alone in it. Bats may use other chambers, but here there is only stone and water. The smell is faintly earthy, like a damp book in a cool room. The air caresses your skin and slips past without drawing attention. The sound of the drip has lost its edges and become a soft metronome behind your breathing. The story of chemistry, of ionic balances and degassing becomes a gentle background. You can let go a little. The stalactite will go on growing whether or not you think about it. It prefers not to be watched, in a way. It is a long, unbroken practice, like a musical drone or the steady tide. There are quiet hazards that the stalactite faces, and even these are subdued. If the cave air dries too much, calcite deposition can shift toward surfaces where evaporation plays a role, and delicate soda straws may be replaced by more granular accretions. If the pH drops because more carbon dioxide is trapped in the cave air for a time, dissolution might happen at the tip, smoothing it or softening earlier detail. This is rare in stable caves, and the cave's own inertia tends to protect it. The rock mass keeps temperature almost constant. The small entrances and long corridors keep humidity high. The slow flow of air diffuses away extremes. The stalactite is buffered by its home, like a sleeping person under a thick blanket is buffered from a draft. In your mind, walk closer to a straw that hangs like a glass string, open at its end. The water that arrives at the top travels down inside the narrow tube, leaving a ring of calcite at the bottom as it falls. The tube elongates, and if left undisturbed, can become very long and thin. If the tube clogs, water may begin to flow along the outside of the straw, and a more typical conical stalactite will begin to grow over it, enclosing the straw inside like a fossil spine. Later, if the outer shell breaks, you might find the hollow straw still preserved, an inner story protected by a newer skin. Helictites provide a dreamy counterpoint. These are thin, twisted forms that depart from gravity, curling in various directions. They grow where capillary forces are strong enough to direct the flow, and where the supply of water is low and intermittent. Tiny films creep along the surface rather than drops falling from an end. As they grow, they turn and branch, making whimsical shapes that resemble coral, frost, or the lines of a pen drawn slowly in the air. The chemistry is the same, but the geometry is different. The result is a sculpture garden of mineral threads in a chamber where silence is preserved like a relic. On the floor, stalagmites receive the drips and grow upward. Where a stalactite drips directly onto a spot, the stalagmite underneath tends to be conical and aligned. Where water splashes, the stalagmite may be broader, low, and spread like a cushion. These forms are the complement of stalactites. Together, they can meet to form a column. Sometimes, several closely spaced stalactites feed one stalagmite, and the result is a column with a fluted base. The diversity of forms is an outcome of slightly different boundary conditions, like variations in a theme. It is restful to think of these as relatives in a quiet family of stone. Now, consider the role of prior calcite precipitation in the rock above. When water percolates and sits in small cavities or along surfaces where it can dig out before reaching the cave, some calcite can precipitate there, removing calcium preferentially and changing the magnesium to calcium ratio in the remaining solution. When that solution reaches the cave ceiling, the chemistry is different than it would have been. The stalactite records this in its trace element ratios. In drier conditions above, water may linger longer, leading to more prior calcite precipitation and higher magnesium to calcium ratios in the stalactite. In wetter conditions, water moves faster. Less calcite is precipitated beforehand, and the ratio decreases. Thus, even without obvious changes in drip rate, the chemistry in the stalactite can hint at broader hydrology. Clumped isotope thermometry adds another quiet layer, where rare combinations of heavier isotopes in the same molecule are measured. The degree to which these heavy isotopes clump together in carbonate minerals depends on temperature, offering a way to infer formation temperatures without assumptions about the isotopic composition of water. Such techniques require careful laboratory work and very clean samples. The data can be interpreted to produce a paleotemperature record, one that is smooth and muted and fits the general sensitivity of cave deposits. It is a serene kind of thermometry, reading the slow dance of isotopes rather than the quick bounce of a thermometer in air. In your imagination, you set a small lantern on a flat rock and sit. The light picks out a few nearest stalactites and leaves the rest in darkness. Your line of sight settles on one and stays. The drop forms, elongates, and falls. Each event is similar to the last, but not identical. The interval between drops lengthens, shortens, then returns. The size of drops vary slightly. The sound on the floor has a dampened thud where the basin is soft, and more of a musical ring where the floor is thin over a hollow. If you close your eyes, the sound becomes a pattern. You can ride like a quiet boat rides small waves. The chemistry continues without you needing to track it. The carbon dioxide continues to leave the drop. The calcite continues to form at a microscopic step. The stalactite continues to become itself. Stalactites can be protected by policies that limit human disturbance. The oils from a hand can change the wetting properties of calcite, altering how drops spread and therefore how they deposit. A broken tip takes a very long time to recover. The carbon dioxide exhaled by groups of visitors can raise the cave air concentration enough to reduce deposition temporarily. Many caves therefore limit visitor numbers and use paths that minimize contact and keep the air still. This care might seem fussy, but it is really just aligning human time with stalactite time, acknowledging that we move fast and they move slow, and arranging for the two to coexist gently. At a deeper level in the rock, below the water table, the chemistry is different. There, the water fills the pores fully, and oxygen is scarce. The carbon dioxide balance with the air is replaced by a balance with dissolved gases. Calcite can dissolve or precipitate there as well, forming other kinds of deposits. But the stalactite belongs to the realm above the water table, in the air, where drops form and fall. That is why stalactites are such pure recorders of the interface between water and air. They are archivists of the Vados zone. There is a neat circularity in the story. Marine organisms built limestone by precipitating calcium carbonate in warm, sunlit seas long ago. That rock was lifted and shaped by tectonics and erosion. Rainwater, laced with carbon dioxide from air and soil, dissolved the rock and carved caves. Inside those caves, water again precipitates calcium carbonate, this time in darkness, reconstructing a small fraction of what was dissolved. The cycle, from sea to stone to cave and back to stone, is continuous on geologic time. The stalactite is a punctuation mark in this cycle, a quiet one, placed in a deep cavern where the world slows down. Think of the numbers, gently. The rate of calcite precipitation on a stalactite tip may be on the order of micrometers per year in some caves and millimeters per decade in others. The drip water may carry a few tens to a few hundreds of parts per million of calcium and bicarbonate. The pH may be near neutral to slightly alkaline. The carbon dioxide concentration in air might be a few hundred to a few thousand parts per million, higher in poorly ventilated caves, lower in well-ventilated ones. The temperature may be the average annual temperature of the surface nearby, within a degree or two. These values are whispers of numbers not to be memorized, but to be felt as the scale of the thing. Nothing here is fierce. Everything is gentle. In some caves, you can see where stalactites have grown past a change in water chemistry that led to a different crystal polymorph, perhaps an interval of aragonite growth wedged between periods of calcite. The boundaries are sharp at the microscopic level and sometimes visible to the naked eye as a change in luster. These layers tell of a time when magnesium was higher in the drip water, perhaps due to a different rock layer being tapped above, or when evaporation slightly increased, perhaps due to a drier climate. Then the cave returned to its prior state, and calcite resumed. The stalactite is an even-tempered narrator, marked by these passages but never startled by them. Powerful floods that change the surface rarely disturb the deep cave. Their influence is felt only in the chemistry of the later water. Dry years cause fewer drops and perhaps more prior calcite precipitation above, while wet years bring more drops and a different balance. Storms that bring dust across continents may add a single layer rich in certain elements. All of these influences are filtered by the rock. The stalactite accepts them and keeps going. The regularity can be reassuring. It is as if the cave says that change is gentle when seen over a span far longer than the day. Now, you might picture the calming mathematical form of the saturation index, which is essentially a measure of how the product of the activities of calcium and carbonate compares to their equilibrium value. When that ratio is greater than 1, the water is supersaturated and precipitation is favored. When it is less than 1, dissolution is favored. In caves, the water that arrives is usually supersaturated by a small margin after degassing, enough to paint thin layers without hurry. If the index is too high, rapid precipitation may make more porous and less ordered calcite. If it is just a little above equilibrium, the calcite is denser and clearer. Again, extremes are softened by the cave and moderate values prevail. The memory of a drip can be trapped in a tiny bubble inside a stalactite. As calcite forms around the drop, a little pocket of water can become isolated, sealing a small volume that holds a miniature sample of what the water was like that day. In some studies, these fluid inclusions are analyzed, their salinity measured, their gases sampled, to glean clues about the environment of formation. It is a delicate process. The inclusion has waited quietly for thousands of years. When it is opened, it releases a story that fits with the broader records. The wonder of it is gentle. It is not shouted. It is whispered in the lab room where the student leans close to the instrument. Let your breathing mirror the drip for a while. Inhale slowly, like a drop forming and swelling. Pause gently, as if the drop considers its fall. Exhale slowly, like the drop descending and meeting the floor. In this rhythm, you can think about the soft bond between a planet's atmosphere and its stone. The stalactite is a slow handshake between air and rock, mediated by water. The handshake is repeated millions of times. Each time a little more of the rock becomes air and then becomes stone again in a new shape. Over a long time, the handshake becomes a column, and the column holds up the roof of the cave like a silent tree. Working from the tip of the stalactite up, the layers become older, and the signatures can be aligned across multiple stalactites to build a composite record. In careful studies, researchers choose stalactites with clear laminae, regular growth, and minimal signs of disturbance. They sample along thin lines with a small drill or a laser, measuring isotopes, or trace elements at precise intervals. The results are combined with independent dates from uranium series methods to construct an age model. The uncertainties are part of the truth. They are embraced, not hidden. The record becomes a soft match between time and chemistry, a map that can be used to see wetter and drier periods, cooler and warmer ones, a picture of monsoon strength or of the shifting edges of vegetation zones. Some caves exist in landscapes affected by people only recently. Over the last few centuries, deforestation or reforestation, irrigation or drainage might have changed the soil respiration and the recharge patterns. Caves under such regions have stalactites that respond. The carbon isotope signature might reflect more or less carbon from certain plants. The trace element patterns might show changes related to dust. But again, the signals are muted by the rock and by time. The cave takes the edge off our rapid changes, for better and for worse. It calms the record to a degree that makes it more useful for seeing the climate beneath the noise. In caves near coastlines, the air can hold marine aerosols that add sodium and chloride to the atmosphere and sometimes to the drip water. In caves downwind of deserts, dust can bring calcium sulfate or gypsum, which may form delicate crystals on surfaces that occasionally dry. These differences make each cave its own world within the general rules of geochemistry. Yet, when we compare many caves, a common language emerges. The basic chemistry remains. Carbon dioxide dissolves in water. Water dissolves calcium carbonate. Water drips. Carbon dioxide exits. Calcite, most often, forms. The stalactite grows. Sometimes the cave hosts moon milk, a soft, pasty deposit that looks like snow or frost. This is made of very fine crystals, oriented in a way that gives the material a creamy consistency. It can coat stalactites and make them look powdered. Moon milk may include a role for microbes shaping the crystal size and arrangement. Its softness contrasts with the hardness of crystalline calcite, a reminder that the same elements can express different textures depending on conditions. The cave curates these contrasts with no need for curation. It is its own museum. The longer you sit with the stalactite in your mind, the more your sense of time shifts. A minute feels like a fragment. An hour feels like a small layer. A day becomes a thin rind that is not yet part of the count. You become aware of how much the serenity of slow processes can ease the mind. The stalactite is always at work, but at a pace that invites rest. It does not ask for attention. It rewards it with the calm knowledge that small, regular actions build big, steady shapes. On the return to the entrance, your steps become part of the cave's memory in a slight way. A little carbon dioxide in the air increases, then fades with ventilation. A small disturbance in the stillness settles back into quiet. Above ground, the world feels bright and quick again. The stalactite remains in the dark, unbothered, repeating its gentle tasks, drip by drip, until you or someone else returns. Before we part, it can be comforting to hold a few images. The soil above the cave breathing, lending carbon dioxide to water. The water coursing through limestone, dissolving a small amount as it goes. The arrival at the cave roof, the drop that forms the gas that leaves, the crystal that grows. The soda straw developing one ring at a time, then sometimes thickening into a stalactite. the subtle bands of color, the interplay of temperature and chemistry, the way the cave air acts like a quiet thumb on a scale, tipping growth a little one way or another. The sound of the drop, familiar now, part of your breathing and your rest. You can let go of the details now. The equations that hide behind these descriptions can dissolve back into words. The words can become images. The images can become a soft sense of cool, damp air and patient stone. If your eyes are heavy, they can close. If your body is still, it can sink a little deeper into the surface that holds it. The stalactite will continue in the dark, and you can drift, supported by the same steady world. If you enjoyed this quiet journey into the patient geochemistry of caves, you can gently press like and subscribe. And if you prefer to drift with a continuous stream of calm science, the playlist in the description is there to carry you along. Sleep well, feel safe, and rest in the knowledge that somewhere in the dark, a tiny drop is falling, and a tiny crystal is growing, and the night is long and kind.